In an earlier lesson, we considered the concept of continuity. When is a graph continuous and when is it not continuous? And what we looked at was three different kinds of discontinuities, okay, three ways that a graph can be not continuous. So let's just review those real quick. And maybe a good place to start would be to talk about what we mean by continuity. When we talk about continuity of a graph, we're really talking about whether it's connected to itself and smooth. And in other words, you can think about this as if I take my pen and just trace along the graph. Can I keep doing this without lifting my pen? And so far the answer would be yes, but now I get to this point, and in order to continue on the graph, I have to stop, move down here, and start drawing again. So I've reached the first discontinuity, and that is a jump that I had to make, a vertical jump, and so we call this the jump discontinuity. Okay. Now I'm going to continue along on my graph here, tracing. So far everything's good. Looks like I'm heading to negative infinity. I'm going to just keep on going way down here all the way to negative infinity. And then I also have to sort of make a jump, although negative infinity is not really a place, it's just sort of as far away as you can actually get. So you could call this a jump, I guess, if you want. But since, okay, then I can continue on. But since we are starting or ending at negative infinity as we make that jump, we call this an infinite discontinuity. Okay. And then finally, I continue along. Everything's continuous and fine. But I reach this point right here where the graph looks like it would continue going except for one point right here that I've taken out. This point 2, negative 5 has been removed from the graph. So I have to stop, lift my pen, move past that one point that's been removed, and then continue on. Okay. Now this one is called the removable discontinuity, and we call it that because we could actually go and put that point right back in there, and then we would have a continuous graph. Okay, so those are the three. That's a little review of what we did. And now what I want to do is to take a look at continuity from the perspective of approaching a point from the left and from the right. We're going to kind of make a little set of rules here that will help us so that we don't actually have to see the graph. We could consider looking at the function definition, and from what we would know about that function definition, how can we tell that it's continuous? So let's go ahead and see what we've got in these cases. For the jump discontinuity, let's start with that guy. And really for all three of these, but let's start with the jump. The idea is that we're going to want to approach, let's get a different color like green here. We're going to approach this point from the left, okay, and by this point I mean x equals minus 8. We're going to approach. And we're going to approach x equals minus 8 from the right. Okay, so from the left and from the right, what's happening here? Well, as we come from the left, it looks like we're going to end up pretty close to 7 for a y value. So let's put 7 down here. Now, because I have this open circle, it's not exactly 7, but in calculus we talk about this as being a limit. And what that really means is what's the absolute limit that I can go to before I get to that open circle at that point. And it's basically the next number past 7, if you want to think about it like that. Kind of a tough concept to think about, but the idea is that we're approaching the value of 7 as x approaches negative 8 from the left. If we come from the right, okay, it looks like we're approaching, and we should hit the y value of 6. Now, what's happened here is if you compare 7 and 6, obviously they are different numbers. If I approach a different number from the left than I do from the right, it's pretty clear that there's a gap there. Okay, it's pretty clear that that graph is broken because one way I'm coming to 7, one way I'm coming to 6, there's this gap in here. Okay, so obviously there's a discontinuity here. Let's take a look at the infinite discontinuity and see what the pattern is there. Okay, so this is jump over here, infinite. And it looks like as we approach from the left, we're heading down to negative infinity. And as we approach, and by approaching I mean negative 3 in this case, if we approach negative 3 from the right, it looks like we're heading towards 4. Okay. And so again, we have a discontinuity because these 2 points, these 2 values obviously are very different. And just like the jump discontinuity, I'm not going to the same place from the left as I am from the right. The only difference really between the jump and the infinite discontinuity is that one or both of these points will have infinity or negative infinity in it. So once again, this is a discontinuity. Let me just erase this a second because I might need that space. Thank you very much. All right, and then the last one that we're going to do is going to be the removable discontinuity. So let's take a look at what's happening here. As we approach from the left, my y value that I'm approaching appears to be negative 5. And as I approach from, approaching again is approaching 2. So as x goes from the left, my y value is coming down here to negative 5. As I approach from the right and go along the graph, approaching from the right, I'm also approaching negative 5. Now what's going on here? We had a discontinuity in these 2 cases because these numbers were different. In this case, the number is exactly the same, but we still have a discontinuity. So it appears that there may be one more thing we need to look at, and that is the case. And what it is that we have to look at is what is the value of the function at that particular value of x. I'll just call it a. So for example, a is equal to negative 8 when we're looking at our jump discontinuity. A is equal to negative 3. A is equal to 2. So what's happening for f of 8 for the jump, f of negative 3 for the infinite, and f of 2 over here for the removable. Okay, so what is happening at f of 8? What's the actual value that's defined here? Well, it appears that the actual value that's defined is going to be where that closed circle is, and it looks like that y value is 6. But since these 2 numbers don't match, I know that this is discontinuous. I was able to call that out before I even worried about what happened here. And the same thing over here with the infinite discontinuity. The value of my function at x equals negative 3, at a equals negative 3, appears to be, right up here, appears to be 4. Okay, let's do it like that. So once again, I have 2 different values here, and so I was able to call this out right away. Now here's where I had the problem, is that I have 2 numbers that are the same here, and so I have to look one level further because I know it's a discontinuity, but this isn't following the same pattern as these guys are. What's happening at f of 2 here? At f of 2, I don't even have a value defined. That's the whole reason I had that discontinuity, is that point has been removed. So I have an undefined value at the function here. And so now I can say it's discontinuous because even though I'm heading to the same place, once I get there, I don't have a number to work with. So I'm going to make a little bit of a contrast here and talk about what happens if I do have a continuous point, for example, right there. So let's say that this is a x value of negative 1 and a y value of, we'll make it negative 2. Okay. So for this point right here, let's just call this point P. So over here at point P, what's happening? As I approach from the left, my value is negative 2, my y value. As I approach from the right, my y value is negative 2. Now that's the same thing that was happening here with the removable movement. When I came from both directions, I was heading towards the same number. The difference here is that if you look at what is the function value here at f of negative 1, okay, what is the function value at negative 1? It is defined, and it's equal to -2. If I pick x equals -1, my output is y equals -2. Look at what happens here with these three. Not only is my left and right equal, which happens to be true here, but the difference is I'm also defined to be that exact same value. And in this case, that's not true. So for a function to be continuous, we want to look at approaching from the left, approaching from the right. We want both of those to be equal, and we want them to equal the value at that point. So basically that says if I head to the same point and that point is there, it's continuous. And that kind of makes pretty good intuitive sense. That's true anywhere along this part of the graph that's continuous. Anywhere along here that's continuous. If I go right here, I approach the point, I approach the same point, and that point exists at that same level.